Hello everyone, welcome to Chip Confessions. As you know all, we have already started with design verification course for batch 1 and we have already completed 2 sessions. So this is the third session, and then in this session we are going to see some common terms before heading towards digital electronics and Verilog. Let us see what are those. First is the number systems. We are just seeing the basics of this number systems and we are not going in depth of it. Let us see just the basics. Then we are seeing the overview of binary data sizes and then logic states and then logic conventions. Let us see them one by one. First is the number systems. What is a number system? A number system is nothing but a way to represent some symbols. Means number system is a system which contains some set of symbols which have some values, and this number system has three major components such as a base or a radix, and then second is the symbols or the digits, and third is the place values. And based on this base or the radix, this number system can be divided into several kind of number systems. Like if we use base 3, then it is a base 3 number system, base 10 number system, base 25 is base 25 number system, like that. No matter how many number of bases we are using, that many number of number systems is possible. But importantly, we will be seeing 4 types of number systems classified based on radix or the base number, that is binary number system, octal number system, decimal number system and hexadecimal number system. First is the binary number system. Binary, in this binary itself we have the word by. By means 2. So we are using 2 symbols here. So the system is base 2 number system, which is also called as binary number system. Means base or radix is nothing but the total number of symbols or the digits we are using in a number system, that is called as base or radix. And for a binary number system, the base or radix number is 2 and we will be using 2 symbols, that is 0 and 1. Next is the octal number system. Octal number system, we are using 0 to 7, that is totally 8 number of symbols. So octal number system is nothing but base 8 number system. Then we have decimal number system, which uses the symbols or the digits from 0 to 9. So in a decimal number system, we are using total 10 number of digits. So this is also called as base 10 number system. Then we have hexadecimal number system. Hexa means 6, decimal means 10. Total 6 plus 10 is 16. So this is base 16 number system and we are using total 16 number of symbols or digits, that is 0 to 9, which is taken from decimal, and then we have extra 6 symbols, that is A to F. Here 0 to 9 represents as usual numbers whichever it is taken from decimal number system, and A represent 10, B is 11, C is 12, D is 13, E is 14 and F is 15. And I am not going in depth with conversions, means converting from one number system to another number system. I hope you all know that, or I expect you to learn that as a part of assignment. But one thing we should know here is converting directly from binary to octal or binary to hexadecimal, that we shall see now, or octal to binary or hexadecimal to binary, how we can do that. Octal number means, as I said, it is a base 8 number system. 8 means nothing but 2 to the power of 3. So To represent any number in octal number system, we will be using at max 3 digits. That is, 0 is represented as 0, 0, 0. Like that, if we go, 7 will be represented as 1, 1, 1. So, to represent any digit in base 8 number system, at max we can have 3 number of digits or 3 number of symbols in binary. So whenever we are converting an octal number to a binary number, what we have to do is, like if we say 137, if we have 137, to convert this to binary, what we have to do is take 7, represent it in binary, take 3, represent it in binary in terms of 3 digits, that is 0, 1, 1, and then we have 1 which can be represented as 0, 0, 1. So this is how we represent 137 base 8 in terms of binary, that is 001, 011 and 111. Means directly we are converting each digit of octal number into binary number. Same way, whenever we are converting binary to octal, what we have to do is, say let us take a number 1, 1, 1, 0, 0, 0, 0, 1. Let us say we have to convert this number into octal. What we have to do is, starting from right side, this is our LSB and this is our MSB. So starting from the LSB, we have to group it by 3 digits. So this 3 digits will be one group and this 3 digits will be one group, and here we have only 2 digits, so we can add a 0 this side and we can make it as a group of 3 digits. So now we can write the number 001 is 1, 100 is 4 and 011 is 3. So the number is 341 base 8. So this is how we convert from binary to octal and from octal to binary. Then we shall see how we can convert binary to hexadecimal and vice versa. If we have a binary number, say 1, 1, 0, 0, 1, 0, 1, 1. If we have this number, let us see how we can convert this binary number into hexadecimal number. As we know all, hexadecimal means it is base 16 and 16 is nothing but 2 to the power of 4. So to represent any number in base 16 or hexadecimal, at max we will be using 4 digits. So whatever the digit we have, we can represent it with 4 digits. Say 0 is represented as 0, 0, 0, 0. Like that, 5 can be represented as 0, 1, 0, 1. Like that only we can represent as F as the last number in this range of hexadecimal. We can write it as 15, that is 1, 1, 1 and 1. This is how we represent hexadecimal numbers in terms of binary with the help of this 4 digits. So while converting binary number to a hexadecimal number, what we have to do is, from LSB we have to group 4 digits, because we are representing each hexadecimal number with 4 digits, so we have to group with 4 digits. We have grouped 4 digits and then again we are grouping 4 digits. We have to see what is this 1011 in hexadecimal and 11 00 in hexadecimal. As we saw, A is 10, which is 1010, and B is 11, which is 1011, and then C is 12, which is 1100, and 13 is 1101, 14 is 1110, and 15 is 1111. So this is our A and this is our F. What we seeing is 11001011. So 1011 is this, that is B, and we have 1100, which is C. So this 11001011 in binary can be represented as CB in base 16 or hexadecimal representation. This is how we converted binary to hexadecimal. In the same way, if we have some hexadecimal numbers, say A, B, 1. If we have to convert this number, this hexadecimal representation into binary, means what we have to do is, starting from the 1, we have to represent it as 4-digit binary number, that is 0001, and then this B as 4-digit binary number, that is 1011, and then this A as 4-digit binary number, that is 1010. So this AB1 in hexadecimal can be represented as 101010110001 in binary. So we got to know how we can convert binary to octal and vice versa. In the same way, binary to hexadecimal and vice versa. Binary to decimal and vice versa, we can convert it by dividing and multiplying. I hope you will take it as an assignment and try from your side. If you face any difficulties in doing that, you can put in the comment box and I can explain it to you in the next session. Let us see what we are seeing now is the binary data sizes. What is this data size? Data size is nothing but how many bits a data is holding. Like if we say 1100, we can say the size of this data is 4 because it has 4 number of digits. Till now we were using either symbol or digit as a representation for a single value. So here we will be introducing some new words which can be represented as symbols with data sizes. So first we have bit. A bit is nothing but a single digit, that is either 1 or 0 is called as a bit. Whatever we were calling now like 4 digits, 4 symbols, 4 representations, that is nothing but is our bit. A bit is nothing but a single digit of data. Means if you say bit, the size of the data will be 1. It can hold either 1 or 0 as a value. Next we have nibble. Nibble is not an official size, but nibble for a 4-bit of data we call it a nibble. So we have nibble which represents 4 bits of data. If I say 1101, this 1101 can be called as a nibble because the size of this data representation is 4 because it contains 4 bits of data. Means the number of symbols or the number of digits represents the size, and based on the number of digits we are giving the names for them. We are seeing them one by one now. Bit is nothing but your single digit data. Nibble is nothing but your 4 digit or 4 bits of data. Then we have byte. A byte is nothing but 8 bits of data or 2 nibbles of data. So if any data which contains 8 bits, it is called as a byte, or any data which contains 2 nibbles, it is called as a byte. So if we have 1101 and 1000, this total will be called as a byte because it contains 8 number of bits or 8 number of single digits or 2 nibbles. 1000 is a nibble and 1101 is also a nibble. So 2 nibbles a byte will contain. Then we have something called as word, half word and double word. Based on the system we are using, this word can take up the number of bits. If you are using a 32-bit system, this word can take the value of 32 bit. If you are using a 64-bit system, then word will take the value of 64 bits. So let us assume we are using 32-bit system because it is more common. So in 32-bit, this word will be having 32 number of bits. 32 number of bits is nothing but your 4 bytes. 4 bytes because if you divide this 32 by 8, you will get 4. So 32 bits is nothing but 4 bytes. What is half word? If we divide 32 by 2 is nothing but either you have to multiply 32 with 1 by 2 or directly you can divide 32 by 2, you will get half word. That is, whenever you are making half of this word, you will get a half word. It is nothing but your 16 bits or 2 bytes. And double word is you are multiplying this 32 with 2 because whatever the thing which is multiplied by 2 will become double of it. So this is your 64. So word is a 32-bit data if you are using a 32-bit system, and half word is half of it, that is 16 bits of data, which is nothing but 2 bytes, and double word is nothing but 32 into 2, that is 64 bits of data, which is nothing but 8 bytes. If you are using a 64-bit system, there this word will become 64 bits, that is 8 bytes of data. Half word will become half of 64, that is 32, which is nothing but 4 bytes of data, and then double word will become 64 into 2, that is 128 bits or 16 bytes of data. So this is how we do the calculations for half word, word and double word. Then comes the term kilobyte. Kilo means usually we take it as 1000, but in terms of digital electronics, kilo means it is not 1000 in terms of bits, because whatever we use, we have to consider the power of 2. So we have to consider power of 2, that is 2 to the power of 10 for kilobyte, that is 1, 0, 2, 4. So kilobyte is nothing but 1024 bytes. Megabyte is nothing but 1024 kilobyte will make your megabyte. 1024 bytes will make you kilobyte. 1024 kilobytes will make you 1 megabyte, and 1024 megabytes will make you 1 giga or gigabytes or 1 GB. Because kilo means it is not 1000 here in this in this digital system. Whenever we use kilo while we are representing data size, it is in terms of 2 to the power of 10, that is 1024. So we will be representing kilo in terms of 1024. So if you say kilobyte, it is 1024 bytes. If you say megabyte, it is 1024 kilobytes. And if you say gigabyte, it is 1024 megabytes. So we learnt what are the types of the data sizes. From bit to gigabyte, we saw everything. Then we have logic states. So in logic states, we have basically 4 states: logic 0, logic 1, logic X and logic Z. So logic 0, basically it represents low. If you are using a positive logic, generally we use positive logic, so by default I am considering it as a positive logic. So 0 represents low or false or off condition. Logic 0 is nothing but you do not have a signal, or a signal doesn't have any value, or the signal is low, or the signal is false, or the value is false, or signal is in off condition. That is what is represented by logic 0 if you are using a positive logic system. Let us see that positive and negative logic system in further slides. So if you are telling a logic 1, then it represents vice versa of logic 0, means opposite of logic 0. This will be either high, or it is true, or it is on condition. This is how we represent logic 1 in a positive logic system. Then we have logic X. This X is also called as either don't care or unknown. What is this X? This X represent either 0 or 1. Means we cannot determine whether it is 0 or 1. It can either take 0 value or it can either take 1 value. That is how this unknown is. Means we don't know. The state is not known for this logic level. Means it can take either 0 or it can take either 1. That we cannot determine. Means the state of this logic level, if it cannot be determined as either 0 or 1, then it is called as X or unknown or don't care. Basically we use this in Karnoff map. If you have seen while doing sum of products or product of sum, there we will be using this. In sum of products, we consider this unknown value as 1, and in product of sums we consider this as 0. So it can take up either 0 or 1 as its value based on its application or usage or the context. Next is logic Z or logic Z, which is represented as high impedance. Means what is high impedance? If we have a wire, in this wire, if the end is not connected to supply, or if the end is not grounded properly, or then we can say this doesn't have any value. Means this wire is floating. Floating means this is electrically disconnected. Means it is neither connected to low value or neither connected to high value. That is what we call as high impedance. Means this has a floating value. This doesn't contain any of the values. No values, either 0 or 1. Means in logic unknown, we saw it can take either 0 or 1. The state is unknown, but still it can take either 0 or 1. But what happens in high impedance is it can neither take 0 nor take 1. Means it cannot take any values. That is what is logic Z or logic Z, that is high impedance. It is equivalent to wire with open end or a floating wire or wire which is electrically disconnected. So we learnt about all the 4 logic states. Let us see logic conventions now. Means, as I said in the previous slide, we have logic high or positive logic and logic low or negative logic. Let us see one by one. Positive logic is one in which we consider 0 as low and 1 as high. So, whatever we do or whatever we assume in our day-to-day life, in the same convention this goes. So this is called as logic high, where high is considered high and low is considered low. This is called as positive logic. Here, whenever you give 1, the circuit will become active, and whenever you give 0, the circuit or the signal will become inactive or low. This is how the positive logic works. And vice versa is the negative logic. Here 0 is considered as high and 1 is considered as low. In this, what happens is the signal is a negative signal. Like if we give 0 to a signal, the signal will become active, and if we give 1 to a signal, it will become inactive. This is how the negative logic works. So, in the logic high, we are considering 1 as positive or high value and 0 as negative or low value. In logic low, 0 is considered as high and 1 is considered as low. Example, if we take a reset signal, if you give 0 to reset, it will not be working or it will be in low condition, and if you give 1 to reset, it will be in active state. That is what our positive logic is. And then for negative logic, reset n we use. Means whenever we are representing a negative signal, as it doesn't follow the normal convention what we use, we have to represent it with a small letter n at the end of the signal name. It will be representing the negative logic. So in this reset n will represent the negative logic signal. Here, whenever we give 0 to this reset n, it will become active, and whenever we give 1 to this reset n, it will become inactive. This is how the logic convention goes. So we saw what is the number system, and then the binary data sizes, and then we saw logic states, and then logic conventions. So these are all the things we learned today, and these were all the common terms which required before starting digital electronics and Verilog. So from next session we will directly jump into Verilog along with digital electronics. Thank you for being with me in this session, and please like, share this video and subscribe to my channel so that you will not miss any updates, and so that this effort will reach maximum people. Thank you so much. Have a great day. Thank you.